Hey, what's happening, everyone? Good to see you here, Kayla. What are we working on today? We've got some new 320 assignments. We've got some 201. I've got some coffee. What are we working on? Take your picks. What do people want to work on? We got Mubot here. Let's give out some points. So let's come to office hours. Points add to viewers. 100 points. Get started. Let me get my Pearson up and going. Oh, wait, that's me about talking. Took the last 2 days off. Yeah, Easter and Dollywood. So I'm just now looking at the new assignment. Awesome. I just posted it last night. So you are in line with starting it up now. Just posted it last night. So yes, I'm getting everything pulled up. It is Tuesday morning. Gosh, everything just goes by so quickly. Like, I think, like, my gosh, it's another week. I can't believe it. Just so much has happened. So much. So quick. Ah! Let's see here. Start. Let's see. Let's open up the new assignment. Let me get that open right here. So, well, thank you so much, Kayla. I really appreciate that. It was a good weekend. We had some ham. We relaxed. Spoke to family. Took some pictures of Bun because he's an Easter bunny, and just relaxed and had a good weekend. With task 1, we created an LM with categorical variables. That is correct for this one. Yeah, let's take a look at that. Let's take a look at making a linear model with. I just finished this last night, so. If there's errors, Kayla, we will find them. If there's errors, we will find them. Okay, let's see. I think I've got the right thing open. I changed all the names of it and everything. Okay, here we go. Let's take a look. Okay, let's hop over to the main screen. Let's do this. So here we are. We'll close out. Okay, cool. And so we have here task 1. Run all this code right here. Close out that graphic. We'll close this already. Okay. So here we are with the new assignment 9. And for this one, so Kayla, I put this in, so I think people will know this. I've been giving everyone a data set, like we've been creating random data sets for the longest time. And I was like, you know what? It's time that I had people actually load the data. So I think people know how to load the library. Yeah, exactly. So I'll go ahead and do that. Like that, I worry sometimes. I'm like, do people know how to load reg class? And then you go data ex2 tips. And this is only for data that's stored in R. So this is data that's actually been like loaded up. So I fear a lot of people are going to get stuck on that. I mean, not a lot, but someone's going to get down here and be like, where's my data? And it'll be like, you have to load the data this time. So these are preloaded data sets. I also want to point this out that this is not, a lot of times if you're working with data, you won't be loading it in this way. These are all data sets that are preloaded into R depending on the packages you have, the libraries, excuse me. So with the library right here, where we get to the new library, it'll tell you what library this is in. Like you'll get to, and it'll be like library such and such. There it is. dplyr has those 4 cats. it's for categorical variables is what that package is called, but it's called 4 cats and it shows cats on it. Forecast package, ggplot2 package. Are we using the entire data set? No random sample. Exactly, we're using no random sample. Good news is I've been checking for cheating this whole semester and there really hasn't been any cheating. There's been like nothing of major concern, like maybe hopefully people are just working together, but I haven't caught any like major cheating. And I've checked, like I've put hours into checking, which I have to do. It's part of my job, like checking to see if people are cheating, but I haven't found anything too major. Like I'm just hoping that people are doing all their own work, which is the goal, which I haven't found any evidence that people are. My contacts are just going crazy. I haven't found any evidence that people are not doing their own work. So, and we only move forward if we have good evidence. So, from what I can tell, people are doing their own work, and I really like that. So, last night when I was making this, I was like, I'm just gonna not use the random sample because I was worried it would have problems. And I was like, I'll just go and use the full data set. Oh wait, this one should not have any problems. Fingers crossed, no problems. Fingers crossed, no problems. There's always problems though. Make a simple linear model explaining tip and include the summary of this model. So this is where you can take your pick. This is a little bit of the randomness here, right here. So this is where I don't expect everyone to do the same thing. So the random sample just would stop people from copying numbers. But if people are doing this to a certain extent by themselves, what you're going to have right here is you're going to create a simple linear model explaining tip dot percentage. You know what I'm going to do? Oh, I've already got it attached, I think. I've already attached this right here. Yeah, exactly, Kayla. That's exactly right, and that's the way it should be, and that's how we learn together. So thank you, Kayla, because that's how we learn, and that's how we grow our knowledge. If you do this right here, it's going to give me an error. That's fine. That error means that I've already got these things attached. When things are attached to the global environment, you can then access them with the autocomplete right here. So that's why I'm getting the autocomplete here. These are now attached to the main global environment. So you might here, I'll show you. I'll detach them. I think we've seen what attach does multiple times, but probably going to have to run detach a few times. There we go. Now it's detached. So now if I type tip dot, they're not there. The reason you might not want to attach stuff is if you have a function with the same name, it'll say it's masked. Like if I make a function, watch this. Just a little bit about attach right here real quick. If I make a function called gender, so gender, make it a function. Make a function called gender. Gender is going to be nothing, doesn't take anything, and gender just returns 2 plus 2. So now gender is a function in the global environment. You can see it right there behind my head. And if I run gender, it's just going to return 4. It returns 4. But now when I attach, because there's already something called gender, it's going to say, oh, it doesn't? That's weird, but now I'm going to have 2 things. If I type gender right here, it's going to show 2 things. Well, that's interesting. Did I misspell? And it's attached? That's so weird. Really? RM. Well, that's weird. I thought it would do something different. Remove RM gender. My brain must there we go. Wait, what? Oh my gosh. Remove gender. There we go. Well, I thought it would do a certain thing, but it didn't do a certain thing, and sometimes things don't do the thing you think they'd do. So we are going to make a simple linear model explaining tip, but since this is a linear model, I wouldn't probably use one of the categoricals. I'd probably use one of the quantitatives. So you could use size of party, and we need to include the summary right here. And there we go. Pretty weak model right here. So we have a simple linear model. You could do different ones. You could find a better one. Like tip percentage is probably more relative to bill in USD. Much better model, 11% of the variation explained right here. So a much better model. Bill in USD. What do we got? Tip in USD. That'll probably explain tip percentage. 11% again. But we have all these variables right here. You can technically... It would be, yeah, let's do visualization 7 after this. You got it, Bailey, definitely. And so we can do this right here. And I'd also, for the goodness of coding, add in data equals ex2 tip. And there we go. So does this make sense right here, Kayla? What are you thinking here with make the simple linear model and then make a multiple model? And so you can technically, I was planning on just using all of them because the shortest way to include all the variables, let's call M multiple. Shortest way to do that is just do this. And there we go right there. So now we have the multiple model and we did not summarize it. Copy paste is your best friend. Wow, look at that. Look at that R squared. The R squared just went insane. Multiple, yeah, tilde dot's fine to do. It's just make a multiple model. So, yeah, multiple models, just multiple X's. And we get a lot in here. A lot of them are not significant, but we do see a lot of significance. And it's so crazy to me. We get such a big jump. You know, we're only getting like 11%, and then we're going all the way up to 73%. Running partial F test to see if the multiple model brings new information. I'm gonna let you kind of talk through this right here, Kale, a little bit. Like, here's the code. So let's read the code as a sentence. The ANOVA, which is the way to analyze variance, we're asking going from the model here to the multiple model, the simple model to the multiple model, does it explain new variation? Does it bring with it new information? And here's the factor increase in the variation explained. And here's the statistical significance going from the simple model to the multiple model. We can also see the simple model right here. There's the simple model, and here's the multiple model right here, rather this right here. So what do you think about this? What do you think going from the simple to the multiple model? This should be a very, especially looking at those R-squareds. I mean, there's a lot of congruent evidence, like things that coincide with the decision I would make right here. I don't want to interpret this too much, but there should be a very, very clear, you can put it in the chat if you want. I might not, I don't know, with what you're thinking, but there should be a very, very, very compelling case to do one or the other. Like it should be like, oh yeah, that's something right there. And what do we mean by that? What does this tell us instantaneously? And this is the eye I'm trying to get with students, especially looking at this right here. Like doing the partial F, you should know instantaneously what this means. Hopefully know, can I create a multiple model with all the variables, analyze it with, see what variables bring no new information one at a time? Well, and so, yeah, you can actually. Watch this. Here's a really cool command. The drop one command, and then actually we need to do test equals. This is at the end of the notes for this new section. So let's explain briefly what this is. This is a little bit beyond this assignment. I think I mentioned in the rubric that people can use the drop one. I think I put that in there. I don't expect people to use the drop one. We'll probably get to this next week, at the start of next week. So what is the drop one? The drop one drops one variable out of the model. And you might say, well, aren't we looking at that up here? We're going to learn something really interesting about indicator variables this week. Notice how over here above my head it says weekday, right? How many levels does weekday have to it? And this is, Caleb, this is the new lesson right here. So it's super important now. I mean, not that you weren't listening, but this is where the new stuff is starting right here, which we'll get to at the very end of today. How many levels does weekday have? And be careful, weekday, you would think 7, but the answer is not 7. Weekday is a categorical variable with how many levels? 4. What do you notice over there? Which this is later in the assignment too. You'll be doing this at the very end of this assignment. The very end assignment, you'll be talking about this right here, how weekday only has 4 levels, or 3, it only has 3, but yeah, has 4 actually. 3, and so what day is missing? We could find out what day is missing if we just go to levels. We can actually run weekday in here. Friday's missing. So Friday is missing. And also, if you look back at your model, the multiple model, how many levels do you see to smoker? Exactly. And smoker only has 1 level. Day, night. Night is the level there. So what level's missing for day, night? And what do you notice? Friday is missing. Female is missing. No is missing. Which level is always missing when it comes, like, you have day and night, and so day is missing. You have female and then male, and female is missing. You have no, then yes, and if you do these right here, the one that's always missing is what? The level that's always missing, the one that's what we call the reference level. The reference level is always the first alphabetical, So the first alphabetical is missing. So the levels to this are day, night, and day is missing. So what we actually have here, the first alphabetical for a factor, and let's say we had all 7 days of the week. How many indicator variables would 7 days of the week create? How many indicator variables, and these, I think these are some of the easiest questions on the test. I love putting questions like this, like we have 7 days of the week. How many indicator variables would it create? I'm thinking of the next question. 7 days of the week, if we had that, which we don't in this model, but if we did, 7 days of the week, how many indicators would it create? If you don't know, it's all right to say you don't know, but once you know the trick, it's like, oh, that's easy. Hint, one of them becomes the reference level. So how many indicators would this create? With 7 days of the week, one of them, bingo, that's it. You have 12 months of the year. 12 months of the year. How many indicators does 12 months of the year create? So there's 12 months of the year. I just don't have enough fingers to do 12 months of the year. You have 12 months of the year. So how many indicators does 12 months of the year create? So to know how many indicator variables it would create 11. And what would become the reference level that all other months of the year would be compared to? what would become the reference level that all other months of the year would be compared to? So you have to think which is first alphabetical. So if I asked on the test, like, what is the reference month of the year? If we make a model, and then, people might guess January because they're like, oh, that's the first month of the year, so it's got to be the reference month. Like, no, that's not how the mathematical models work. They don't have any preference for what comes first. I mean, you can assign it April. Yep. I was like August, April, and I was like, which of those is first? And I was like LMNOP, QRS, TV. Yeah. So it'd be, if we made a multiple choice, it might not even include August. I might just be like April, September, December, January. And, people are like, April is the answer because it's first alphabetical. That's how our models decide. And there's no real reason for it. It's arbitrary that it's first alphabetical. It's just you can then know which it is because you're like, okay, whichever is first alphabetical becomes the reference level. And it doesn't matter. All other levels are just compared to it. So if we're predicting right here, and this is literally for this week, like here's a hint for later on, we're predicting tip percentage right here. Down lower, you'll do bill instead of tip percentage. But with using tip percentage, 2 days that are otherwise identical, but one day is a Saturday and the other day is a Friday, the day that is a Saturday is expected to have 25.25 more tip percentage than the Friday. So 2 days that are otherwise identical because it's a multiple model where one day is a Saturday and the other day is a Friday. And this is why it's called the reference level. So think about what it means for something to be the reference. It's like the point at which we're comparing. So if I make a model that predicts my age, like if I have a model that that explains age, we could have here Brian. Brian is going to be 0 because he's the reference. Then we have Darren, and Darren's going to be 2, and Emily, and Emily's going to be -3. So let's do it this way. So if Brian is 39, how old is Emily? So this is how these reference level things work. Brian is 39. How old is Emily? Brian is 39. How old is Emily? Oh, that's awesome. Yeah, my sister's Emily. There you go. So shout out to Emily right there. 36. And why does Brian's the reference, so we don't even include Brian in the model. Sorry, Brian, you got to go. We don't even include Brian in the model because he has no coefficient. If we included Friday in the model, Friday would have a coefficient of 0 because we're saying how different from Friday is Friday. So it's the reference level. It's just that Darren is 2 years older than Brian. Emily is 3 years younger than Brian. And so we include those in there because they don't have coefficients of 0, and we don't test for like the difference from the reference level. It's important to note also what you're seeing right here is these p-values right here are the significant difference from the reference level. So when you see this right here, Saturday is not significantly different from Friday. Sunday is more significantly different from Friday. If you ever worked in a restaurant, a lot of people might tell you, Sunday is a very unique day, but Thursday and Saturday are very much like Friday, apparently, at least when it comes to this variable. Sunday is the most different, still not statistically significant difference. But that's the difference from the reference level when you look at these right here for multi-level indicator variables. That brings us back to the drop 1. So what does the drop 1 do? The drop 1 is actually running a partial F test. So it's actually removing out, look at how many things it removed out when it removed weekday. How many variables did the drop 1 remove out when it removed weekday? And so I'll let you, it's kind of like creating a normal model that becomes yeah, exactly. It's like that's the center of the model and the reference, and that's where we're comparing to. Yep. And the drop 1's doing the partial F's for us right here. Like the drop 1 just did a whole bunch of partial F's, which the only one to really care about right here is weekday. And so it removes the 3 indicator variables because the reference level doesn't really have a variable to it. So these are the 3 variables in the model right here, and the reference level it doesn't exist. The reference level doesn't exist, and so we have right here the 3 indicator variables are removed out. So it doesn't even keep the reference. Nothing stays in the model. So there'd be no coefficients in the model for this variable. So it takes everything out of the model for this variable, and then it looks at the model with and without this variable, and it gets the p-value to see if the variable adds in new information. You know what's really interesting? This p-value here of 0.067, this p-value of 0.067 is actually, and actually here, I'll do the one this is something I found out last night when I was working with the data. So I'm kind of doing number 3 right here to show something interesting. We'll open a new sheet so people don't think we're doing that one right there when they watch this video. Okay, watch this. Okay, good. I didn't mean to do this. We've done a lot of the assignment already. Okay. Look at the p-value for all the days. The p-value for all the days, but this is the difference from, this is kind of, this is the last, this is part 3 right here. The p-value for each one of the days is not statistically significant. The p-value for each one of the days is not statistically significant. But the p-value for the model is statistically significant. And if we do drop 1 right here, we're actually comparing it to the what? And let me put in the test equals f. You don't have to do this here because you'll see, I can tell you the p-value. The p-value for the drop 1 is going to be this. And there it is right there. The same p-value up there is this p-value. So if we drop weekday out of the model, we're actually comparing it to the what model. If we were to drop all the things for weekday, like weekday has 3 levels, and if we were to drop all of this out of the model, we're actually comparing it to the what model. If we drop weekday completely out of the model, like we take all of that out, then we're comparing it to, we're comparing it to the naive. And that's what this does down here. This is the ANOVA down here. And so the drop 1 right here is actually comparing this, because it just drops 1 variable out of the model. So it's going to drop weekday out of the model, and then you have the naive model. So the p-value right here is the p-value right here, because this is the ANOVA, which is comparing the naive to our current model. Does this all make sense, Kayla? Like, this is a much deeper, better understanding right here. And it's like, oh, that's why that p-value is the same, because the drop 1 is removing one of the variables, like a whole of it. It's not removing one of the indicators. It's removing the variable weekday from it. We could add in more variables here and do a more complex model, but the drop 1 right now is serving the same purpose as the full ANOVA. Yeah, and if you're getting that, you're really understanding what the point of the drop 1, or at least what the point of a partial F test is. And I really like, the drop 1 is such a great way to do partial Fs, because if you have multi-level variables, you can just do the drop 1 and it'll take out multiple variables. But the big thing this week is going to be understanding how these indicator variables work. And let's do one last part of this. We've done a lot of this assignment by now. One thing that really might confuse people, and I want to show how to do something cool, is if we want to write this model right here, watch this. I'm doing way too much of this assignment. No, be careful. I can't remember which way it prints. Please, please, please listen to this. Look at your output afterwards. I can't remember which way shows up. I feel like one of these doesn't. We are predicting bill in USD, so that would go there. Bill in USD equals, ooh, see those underscores we don't want. We don't want them. Look, watch whatever this is doing. Bill in USD. And then we just take this right here. We take the intercept. We drop that in. We're just going to go across this real quick. And there we go with those. So there's those values right there. The weekday Saturday. Let's put a plus right here. And then I'll put it this way because we're supposed to do, oh my gosh, it's going to be so crazy long. We don't like that. So does this make sense here, Kayla, what I'm doing? We talked about this yesterday in class. We'll talk about it today too in class, that you're just taking the coefficients and timesing them by the variable. So you want to take the coefficients times it by the variable, and this will get you the model right here. And this is how you write LaTeX. Just creating the equation, exactly. That's all you're doing is just writing the equation. You could annotate down some decimals. I'm trying to get it so it'll fit on one screen. Graders should not care if you annotate to 2 decimals. Whenever I write equations, usually I use 2 decimals, as long as I'm not doing p-values or something. So that'll write the equation, and there we go. And what, I'll ask this question to you, Kayla, and I can't remember which way it prints out. Like, let me take a look. I'm actually I'm gonna knit this and see if, because that does that, and I feel like you have to do the double. I can never remember. So let me pause screen for 2 seconds, and let me knit this and see which way it looks proper. Knit to HTML. Wait, we're doing, if I knit to HTML, it might do something else weird. Let me knit to Word, because you guys knit to Word. Doesn't it? Okay. Here it is, and it did both. Oh, no, this one didn't. The single one didn't. I was right. The single one did not show up. And the bill in USD on this one, if I'm printing this out, I'm going to decrease font size. There we go. I'd make it look like this. It's a little small to read, but at least it's on one line. I I mean, you could change that to Saturday. I think, I don't know, maybe I'd keep it. The graders should not care. It's everyone should know, like, you're predicting for Saturday, and now you could increase font size. I might, if I'm presenting this, especially because people would know the context of, like, what is a Thursday, what is a Sunday, what is a Saturday. They would know this. So this is not the right way right here. That will show up when you do it here. Like this shows up right there, but it's the double dollar signs. You have to use double dollar signs for it to show up. I knew it was one of those two ways. I just want to make sure I did it properly. But knowing how to write equations will be big for the final. Like knowing how to go through output. You look at, I think it looks better without weekday too. It just makes more sense. Like it makes more sense right here to not include it. So you could narrow this down right here. And you also get the preview of it, which is nice. Now, what bill in USD would we predict for I can't even think, for Friday? What bill would we predict for Friday? What amount? So you can look at the equation right there. What amount would we pick? What amount would we predict for Friday? And here's how to work this equation. If we're predicting for Friday, well, then this becomes a 0, this becomes a 0, this becomes a 0. It's like, do you ever tell your kids to turn off the lights, or like when you leave a room, writing equations? Yeah, exactly. So these are indicator variables, and they can only take on the values of 0 and 1 because it becomes a 1 when it is that day. So hopefully that makes sense right here. Like if it is that day, it becomes a 1. If it's not that day, it becomes a what? And you can kind of see it mathematically here. So when you think about it mathematically, it should make sense like how it works because exactly. So what would you predict for Friday? What bill in USD would you predict people have on Friday? What bill would you predict that people have on Friday? Well, it wouldn't have 0 bill on Friday. You're close. 0 is what's going to go into the X variables for Saturday, Sunday, and Thursday. But you might have been responding to the last question. So we make a prediction with the model by going through and putting in 0 for the days that it's not and 1 for the day that it is. Were any of these negative coefficients? Oh, no, they're all positive coefficients. Only 0 and 1 because it's categorical. Exactly. That's like true, false. Exactly. That's the way to think about it. It's like it can only be this day or not this day, and it can't be 2 of these days. So you notice here there's only 4 levels. 0 is for the last. So 17. Exactly. Because once you put in 0 here for all of these, they'll just 0 out. And that's just 0 times this plus 0 times this plus 0 times this. And you get this right here. Now, when you think about this just conceptually, Saturday, here we'll make don't make it this, but here let's make our lives super easy. This makes our lives really, really easy. This is not the equation, but this just makes life a lot easier to talk about. So it's exactly, the intercept is the reference. This is when all reference levels are true. In this instance, we just have one reference level, but this is the value for Friday because we're making no change to the model. So does that make sense right there, Caleb? Like if I ever said for this one, if I said write the implicit regression equation for Friday, that would be it right there. Because all you're doing is going in, we change the numbers to make it easier on ourselves. You just go in and you put zeros for these, and then you solve the equation. And so all you need is the intercept. So here, let's do, here, we'll wait 1 second. So what would we predict for Sunday? What would, use the top model, which is just an easier version of the model down here. We just made the numbers nice. What would you predict for Sunday? What would be the bill in USD that you would predict on Sunday? What bill in USD would you predict on Sunday? And then we'll look at that, how that mathematically works out here. What bill in USD would you predict on Sunday? Exactly. And all you're doing is going in here and doing the following. So you're doing this right here, and then you would solve it out. You would just reduce the mathematics down, and you're just mathematically doing this right here. I forgot the plus. So you would get 21.00. And that's going to be the equation now, just a very simple version of it. And so let's look at a more complicated one. Here's the more complicated one. I'm going to ask you a pretty crazy question right here. Watch this. Let's go up to and then we're going to hop over to the visualization here in a moment. Okay, here's the multiple model. Write out, we don't want all those. No, is there only, that's such a bummer. Let me do this. Sure. Write out the equation for a female paying the bill who's a non-smoker on Friday. And listen to what and so first thing, just identify, this is how I'd make a question like this that is a lot longer, but much easier to do. Write out the equation for females paying the bill on a Friday who's a non-smoker. And what do you notice I'm asking for right there? Everything I'm asking for is the what right there. And I'm going to start writing the equation while we see this right here. Everything I'm asking for is the what when I say a female paying the bill on a Friday who is a non-smoker. So we're predicting tip percentage. A female paying the bill on Friday who's a non-smoker. Everything I've asked for right there. And this is where if you get this, you're like, oh, that's really easy. You're like, okay, I get it. Well, oops. It doesn't like these. Sorry. That's in LaTeX, that's used for like lower writing. There we go. So female is the what level of this? Female is the what level of this? Female is going to be the what level for gender? Female is going to be the what level for gender? There's indicator variables, and then there's a what level. It starts with an R. It's the one we compare everything to. So female will be the what level for gender? It'll be like the reference, exactly. So what are we going to plug in for gender male? Because this person is not gender male. So basically, we're going to plug into this not gender male, which means for gender male, we're going to plug in a what? So for gender male, we're going to plug in a, like if I were to write this up here and I were to do plus something up here, gender male would have a coefficient of what? Since they're not gender male. Because they either are gender male or they're not gender male. Exactly. And this person's not gender male, so we plug in a 0, and anything times 0 is 0. I also said they're not a smoker, so what am I plugging in here? I'm plugging in 0, and remember how Friday was the reference level below, so we're not going to plug in, we're going to plug in zeros. Great job, Dylan. We're going to plug in zeros for all of these right here. So guess what? Everything from here below has a 0, and do you notice how all I did is have the intercept right here? And if you notice, all this does is change the intercept to the model. We can look at that here in a moment visually. But I've actually written out the equation. That is the equation right there for females paying the bills who are not at a non-smoking table on Friday. Does that make sense that the reference level now, exactly, and I think you have it right there, Kayla, the reference level now is females paying the bill on Friday on a non-smoking table. So because we have to acknowledge each one of the reference levels for each one of these. Is that making sense, Kayla? How this equation right here is the implicit line for that. You could show it mathematically if you went and started adding in things like gender male and add the coefficient. But when you solve it, oh, it's a negative coefficient. When you solve it, if you were to go through and solve this, this equation right now is for the reference levels, and then you could change it to the male equation by plugging this in and then solving it out. This would change the intercept right here. Where's my minus sign? Oh, it is there. I can see it on the top screen. That's weird. But now if you solve out this would solve out to the equation of the line for males. I mean, yes, for males, correct. And then you would just take right here, and you would go and you would subtract off this. And now that is the coefficient here, or the intercept. We could have done that. That is now, this is now the equation for males. Yeah, I know, right? It's like once you see it, you're like, oh, then we just subtract off. So you could, if you understand the mathematics well enough, you can just solve out. You could just be like, well, we need to add this because all you're doing is just adding to the intercept. And let's look at this visually right here. What you'll notice is, where's our other model? Where did we make that model? We made it on the other tab. That's where we made it. Watch this. Cool. Let's go make a visualization of this. And you'll see the only thing that is changing, is the what? The only thing that is changing between these models is the what, Kayla? Like you were mentioning it earlier, and you can see it here visually. The only thing that is changing between these models is the what. So you have 2 days that are otherwise identical, like they have the same tip percentage. This one has a 20 tip percentage. This one has a 20 tip percentage, but they're otherwise identical. But one day is a Friday and the other day is a Thursday. And that actually has a very, very small difference. The only difference between these, look at the summary. Thursday should have a very small coefficient. What is the coefficient of Thursday? Yep. And you can see it here. How did I know Thursday has a very, very small coefficient? How did I know Thursday has a tiny, tiny coefficient? How did I know Thursday is going to have a ridiculously small coefficient? And I could have told you what's the green line. Sunday. Sunday has the biggest coefficient. How do I know these things? Exactly, the intercept difference. And how do I know that Thursday has such a small coefficient? It's very hard to see. I mean, it almost looks kind of crazy right here. How did I know that Thursday had such a small coefficient? You can see that blue line right there. There's another line. So how did I know Thursday has such a small coefficient? Because the coefficient of Thursday is based on what? How did I know Thursday? And then Sunday has a much larger coefficient. Sunday's all the way up here, has the biggest coefficient. Saturday is right here, and Saturday has a decent coefficient. And how do I know that these coefficients, like I could have told you Thursday has the smallest coefficient by looking at this. Especially if we put this and we say, which day has the smallest coefficient in this model? And so like in terms of absolute value, because it is hard to see which line here. And so kind of, so what line, and it's not because it's below all the other lines. It's very hard to see maybe, but there's a black line right here, and then there's a blue line. And the black line is the what level. The black line is the what level, because it's Friday. And notice Friday has no coefficient. Friday has no coefficient in the output over here. So that means Friday especially, and it always codes that level in black. Friday, and these are the reference, exactly. The black is the reference, and then the blue is the closest to it, the red is the second, and then the green is the furthest away. So in terms of how far they are away, these are the differences in intercepts. If we go back here to the start of this, does that make sense, Kayla? These are the differences in the intercepts between the lines, and there's no, like the intercept for Friday is this, but then the intercept for Saturday is that much higher, the intercept for Sunday, because they're parallel lines. Now there is something we can do. If you want to change the slope, do this. Now you have different slopes. Allowing them to interact means the impact of tip percentage depends on the day of the week. So the way in which tip percentage explains the bill depends on day of the week. And I almost put this on the assignment, and then I said, no, let's not. So now the slope of the line is also dependent on the day of the week, because the slope is the coefficient of tip percentage. So the way in which tip percentage explains the bill in USD depends on the day of the week. And this is within interaction, which allows the coefficient of tip percentage to change based on the day of the week it is. And you can see the differences in the slope. And the more drastic the differences in the slope, the bigger or the more significant the interaction. The visualization does give us the p-value, and it's super not significant. I know these lines look like they're not very parallel, and they're not. I mean, either lines are parallel or they're not parallel, but it's not significant enough. This is probably just due to random chance. Is this making sense here, Kayla? So only if you do an interaction would you be able to change the slope of the line dependent on what day of the week it is. And I did that by just doing the multiply instead of the add. And now I have, a interaction model with indicator variables, which is probably the start of next week. And we'll be more on the next assignment. Yeah. But if you don't put the interaction here, you only change the what. If you don't put the interaction, you only change the intercepts. So because you're just doing a constant change, it's just a constant addition. If you go back to the mathematics we were doing, it's just a constant add to the model. When you talk about if someone, is male, or if they came in on Friday, it's a constant change to the model, like a constant degree difference of a certain amount. Do you have any more questions, Kayla? We'll probably do visualization 7 here. But this was a really good 40 or so minutes going over everything, or a good part of the assignment. I mean, that should be enough for everyone to get a really good start on the assignment, I would hope. But yeah, if you have more questions, let me know. We're going to talk some visualization number 7. Let's do this. Visualization number 7. I don't know. It's like, I can't wait till summer. Visualization. We have 2 more visualizations left. Oh my gosh. We're almost done right here. Let's see. You're welcome, Kayla. Great job. No, excellent work. Excellent work. I'm really proud, like, people starting early, being like, hey, we just got the assignment, let's do it. Because, a lot of people start early, so it really helps. So thank you, for Kayla, for showing up. Hashtag show up. We all know that. And checking out some of the work. Let's check out some decision trees. Let's throw out some more points, too. I love seeing people get more and more points. So points, add viewers. 200 points. Why not? So using decision trees, data set, take a random sample of 300 plus the last 2 of your student ID. If your UT student ID ends in 23, it'd be 323. Assume for this exercise that the population size is 4,122 students. That's going to help for the 10% condition. Confidence interval. Note the population of interest here is stat to 1 students. The parameter of interest is the proportion of students who plan to take out student loans. Creating 98.5, nice job, Kayla. 98.5% confidence interval. Include a short write-up of the 3 conditions one must check. Clearly indicate whether the conditions are met or not. Regardless of these conditions, provide the interpretation of the confidence interval. Include the 4 generic parts of a confidence interval. Okay, got a lot to do right here. And then we're going to do a confidence interval for the mean and wants 94.5%. So make sure you do 94.5. Okay, so let's go ahead and download the data set. Let's go ahead and open up here in JUMP. Got the data set opening up. And here we go. I am doing different variables. Let me type this out so people realize this. So I am using different variables. I am using different levels of confidence. Make sure to follow your instructions. I cannot highlight this enough. Someone's going to skip through and not see this. So like, no, and then they'll be like, your video. And I'll be like, I'm sorry. So make sure to follow your instructions right here. I'm using different variables. I'm doing different percents, but the concepts still hold. The important thing here is to learn the concepts and to know the concepts behind what we're doing. So let's do the concepts. So we're going to take a random sample of 300 plus the last 2 of our UTID. Pretty basic, right? I mean, like, I can do this. 300 plus the last 2, that's way more than the last 2. 3, 2, 1, that's awesome. Okay, make sure to put in the last 2 of your UTID, and you should see down here in the bottom corner, 300 plus the last 2 of your UTID. So we're good on that. So the first one is a categorical variable. We're going to go up here to distribution. Can't even think what it's called. Analyze distribution. With analyze distribution, we're going to select it, and then we're going to select a categorical variable, but you need to use the one that you're supposed to use. So use student loans. So you can see right there, student loans somewhere on here. Where's student loans at? There's student loans. I'm going to use, let's use Greek life. Okay. Make sure to do the variable that you're asked to do. Do not do the one I'm doing. Once again, let's show it again. So I am using different variables. I am using different confidence levels. Make sure to do the ones you're supposed to do. Here we are. We're going to go to the red arrow and go to stack. Stack just turns it horizontal, so awesome. You can also change the size of this a little bit. I'm going to make it like this. I don't know. I just think that looks nicer. You can do anything. You can change the histogram colors, histogram color. You can make it favorite color. Let's go here to purple. Let me go to every color we want. Now that we have this, we're going to add in one or two things. Don't click the data. If this happens, that happens to a lot of people. You can go here to row and go to clear row states. That was just an accent, but that can happen. Just go to row at the top. It's this little bar. On a Mac, it should be way at the top right there if you ever have data selected. Someone's like, whoa, I didn't know that. There you go. Knowing's half the battle. So now we are going to add in a few extra things here. We're going to go to histogram options, count axis, and that makes it nice and pretty right there. So we've got everything good to go. We just need our confidence intervals. So to get the confidence intervals, we're going to go to the second red arrow. We're going to go to confidence level, and then we're going to go to other. Make sure to put in your correct level of confidence for this. This is going to allow us to choose the level of confidence. I'm going to go ahead and put in 99%. Okay, someone's, I don't know, worried. I don't want people to put in the wrong amount. That's 98.5% confidence. So this is 98.5% confidence. Let's kind of isolate it on the screen right here and make sure to follow your instructions. Always look at your instructions. So here we are with 98.5% confidence. I guess we could just screenshot it, right? Yeah. Let's go here to screenshot. Take some great screenshots. There we go. Perfect. Love it. Excellent screenshot. So when it comes to the conditions, okay, let's review the conditions right here. The conditions we have are threefold, at least at this point. We have three conditions. Condition 1. So condition 1. Random. It is met because we took... I don't think there's a comma there. Condition 1 is met because we took a random sample. Good girl. Condition 2 is 10%. Or we could say less than 10%. Less than 10%. Is it met? I'm gonna let everyone think over this. This is one people often get wrong. So I'm gonna let you think this over. I'm gonna let you look at the instructions right here. I want you to look at your sample size of 321 or whatever yours is. And then I want you to take a look at this right here, and I want you to think it over. So I don't want to, this says the population size is this. So I want you to think it over. You can ask questions in the chat. You can always put comments on the video. But I want you to think over here. You took a sample size of 300 something, and then we're saying assume the population size is this. So I want you to think it over and be like, okay, is it met? So then the last condition for this one is going to be, maybe we'll just write it out, but I don't know. Either which way. Condition 3 is going to be the success failure condition. And I want to point something out right here. And is it met? Well, we need at least 10 successes and at least 10 failures. And I would quote the numbers. I'm pointing out something right here that this is how many successes we have, and this is how many failures we have. I'm going to grab something off the Discord right here. Not there. I'm going to grab something off the Discord. We have a cheat sheet for conditions. And I know a lot of people generally get stuck on conditions. So I'm going and grabbing the cheat sheet for conditions right here. And there's that. Okay. So the cheat sheet for conditions is the following. This is our cheat sheet for conditions. So hopefully some people are checking this out. And this helps out with studying for the final and knowing which conditions to use and when. Condition 1 is always that we randomly sample. Condition 2 is less than 10% of the population is sampled. And then we pause and we ask, what kind of data are we working with? This time the answer was categorical, which I have here in green. Since the answer is categorical, it is success failure. We need at least 10 successes, at least 10 failures, and then there's no other conditions. If we have quantitative data, then we use the nearly normal large enough n condition. We'll be talking about that in a moment here. The last condition right here, the expected cell count, is for chi-squared test of independence. It's also, we have the count data. But we only get to a fourth condition if we have two variables, which we will have when we have independent means. And this is for quantitative data, hence the color coding of blue here also. And then the fourth condition right here for chi-squared, which is count data, which means we have two categorical variables, and independent means means independent means. More on those later, but not today. When we interpret a confidence interval, do I have a confidence interval interpretation blank ready to go? I am blank percent confident. Oh, nope, that's the wrong one. Let's do it. Let's write it out. I am blank percent confident that the true is contained in the interval blank to blank. I am blank percent confident that the true blank is contained in the interval blank to blank. So these are the four parts. This part is the easiest part. I am this percent confident. I am this percent confident. The next part, that the true blank, is where people usually make a mistake. But what are you trying to estimate? I'm trying to estimate the true proportion of students who are in Greek life. And this is proportion because it's categorical. Always read it out loud and see if it makes sense. I am 98.5% confident that the true proportion of students who are in Greek life, that makes sense, because categorical, the proportion of students who are in Greek life, is contained in the interval 31.98% to 45.07%. So you notice right here, here's the lower bound and the upper bound. So this is the lower and the upper bound, and this is the p hat right here. That is the sample proportion, which is also over here. That is the x, which is the number of successes, and this is the n, which is the sample size, and this is the non-conforming portion. So we have right here all of this, and understanding this output is very important. And we have the lower bound and the upper bound for the 98.5% confidence interval. So when you plug these in, make sure to say, I am blank percent confident that the true blank is contained in the interval blank to blank. This is where the mistakes happen, but this is just what are you talking about? I am talking about the true proportion of students who are involved in Greek life. And that's usually people put in true mean. Make sure you think like, what am I talking about here? I'm talking about students in Greek life, which is a categorical question. By using the success failure condition, we are acknowledging it is categorical. For the next interval we're doing, we need to do a quantitative interval. So let's go grab our data here. Let's go to Analyze Distribution. And with Analyze Distribution, we are going to do, let's do the number of, let's now go on, weekly hours at a job. Oof, that's very skewed. You know what? Let's do that one. Analyze Distribution weekly hours at a job, and I'll explain why. So when we do this one right here, we go to Analyze Distribution. We put in our quantitative Y variable. We click OK. We're going to click the top right arrow. We're going to go to Stack. We're going to go to we can click the histogram. We don't have to do these things, but we can if we want. We can go to our favorite color. There we go. We can go to the second red arrow, go to Histogram Options, Count Axis. Always good to have a count axis. We can change this a little bit here, make the size we want. Looks good to me. And then last but not least, we are going to go to the second red arrow here, and we're going to go to confidence interval and the percent again. So make sure to select the proper percentage, and we're going to click here and type in something like 94.5. We're going to click OK. This creates the interval. And I'd probably take a screenshot of all of this. You know, maybe the way I might do this is I might not want that long of a screenshot. If I'm screenshotting this, I don't need that distribution thing. I'm going to select this right here. There we go. And then I'm going to go back to my Word document. I'm going to put that in there. And then below this, I'm going to put in, let me center it. I could center this too. There we go. And below this, we're going to go here. And we're going to take the confidence interval. We can always, I don't like that I got that little bit. Always take the best screenshots. There we go. I love that screenshot. Amazing screenshot. Let's bring down the size on this a little bit. There we go. And here we are. We've got the information needed. We've got our histogram. We've got quantiles. Great. But you notice this is very skewed. Let's go talk over the conditions right here. And the conditions, you can see, are random, 10%. But then we need to pause. And let's delete this one right here because now we need to ask what data are we working with. This data we are working with is quantitative because we're asking how many hours a week do you work, and it makes a histogram. Notice how histograms are quantitative, bar charts are categorical. Even though it does say histogram as options on this, this is a bar chart. The histogram right here is quantitative. It has the quantitative scaling to it. So we have a histogram right here. And we have here our confidence interval, and then we have the third condition. Since it is quantitative, the quantitative is going to be the nearly normal large enough n condition. I kind of combine them together because we're asking, will the distribution of the mean be nearly normal if the sample size is large enough? So a big important concept right here, let's show this. The central limit theorem comes into play. And where is it? Here it is right here. We have a very, very skewed distribution. Our distribution is very skewed. It's even more skewed than that. We could go here. And this is our shape of our parent distribution, something like this right here, ridiculous. And then we are taking a sample size of 200. Oh, I just clicked wrong button. We are taking, hopefully, literally heard the computer spinning up when I clicked that. Loaded up OBS. So we are taking a sample size of 300 something, which we can't even simulate here. But we're talking about the mean of 300 observations, 321 observations from a sample of this. Of 4,000 something. Now, if we did this repeatedly, the new distribution would look more normal and tighter, and we have to ask, is the sample size of 25 large enough? The way this condition works is we have certain numbers that we use, and I've got them over here in the notes. Hey, Mr. T. Here are the numbers right here. No, that's the conditions, and here are the numbers right here. I go to lecture screen. There we go. So the numbers are 1, 25, and 100. And notice for the nearly normal condition to be met, n needs to be larger. We need to have a large enough n. So since our distribution is very skewed, we look at our shape of our distribution. Here, I'll show that again right here. The shape of the distribution is very skewed. We can see that right here. It's very skewed. Since it is very skewed, we need to have at least a sample size of 100. And do we have that with this very skewed distribution? Do we have a sample size of at least 100? We do. We have a sample size of 321. So that's what we need to state. Here, I'm going to say it here, but I'm not going to write it down. But I would say my original distribution is very skewed. Since it is very skewed, I need a sample size of at least 100. My sample size of 321 is large enough for the distribution to be nearly normal. And either one, I'm probably just going to call it nearly normal / large enough n. I just like combining them together. Nearly normal / large enough sample size. Oops. There we go right there. Is it met? Yes, it is met. And why is it that one? Because we have quantitative data. That's why we are doing this right here, quantitative data. And we'll make that lowercase m because it's sample size. Here we go with reading off the interval and explaining it. Let's go back up to here. Just for the moment, I'm just going to show this. So I would include that other bit of output. I'm just showing this so we can just focus in on it. I am 94.5% confident that the true mean hours, because we're doing quantitative, so this is mean, the true mean hours worked per week for UT students is contained in the interval 6.899 or 6.9 rounded to 9.22. I am 94.5% confident that the true mean hours worked per week for UT students is contained in the interval 6.90 rounded to 9.22. And why 94.5? The percent confidence right there. I think that's got it. I think we'll be back later. Is anyone else here right now? We've done some 320 and we've done some 201. I'm going to start preparing for class. Drink some more coffee. We'll put on some music right here. A little music. Ever space. Back in space. Get ready, everyone. Lots of learning to come. Oh my gosh. I hope I'm not getting sick. No, can't get sick. Semester's not over. There we go. Way better now. I'm 100% now. Totally healed. Fine. Just need to get my second cup of coffee. But with that, we will be back later. Office hours in the afternoon, 3:20 to 01. Keep working hard. Assignments are coming up. I will talk to everybody later. But bye for now. Bye. Bye, everybody. Be back later.